means n has to be equal to 4. Now, notice that we started at 0, so n equals 4 is actually the 5th term. So we need to use 5 terms to be able to estimate the sum to within 0.001 units away from the true sum. Now, it also asks us to find that sum. So in order to find that sum, we're going to do the sum as n goes from 0 to 4 of -1 to the n over 2 to the n times n factorial. And we sub in the values. We're going to get the same numbers that we got here, but we're going to alternate sign. Now when n equals 0, we're going to have a positive. So we're going to start off with +1 minus 0.5 plus 0.125 minus 0.02083 plus 0.0026, which is going to be approximately 0.60677. So there we figured out how many terms we would need in order to approximate the sum to being within 0.001. So we needed to go to where n was equal to 4, but since we started at 0, that really meant it was the 5th term. So then to find the sum, we calculated the sum as n went from 0 to 4 of -1 to the n over 2 to the n times n factorial, found those values and approximated it to 0.60677. Okay, and the final thing we need to talk about with alternating series is absolute versus conditional convergence. Absolute convergence is when the series converges for the absolute value. So if the series, the sum of the absolute value of a sub n converges, the series a sub n also converges. So the sum of a sub n is absolutely convergent if the sum of the absolute value of a sub n converges, and the sum of a sub n is conditionally convergent if the sum of a sub n converges but the sum of the absolute value of a sub n diverges. So absolutely convergent if the absolute value converges, so if you don't need the alternating piece in order for it to be a convergent series. Converges conditionally if it's only converging because of the fact that it's alternating in sign. If the series would not have converged if it did not alternate in sign, then it's considered conditionally convergent. So we're going to determine whether each series converges conditionally, converges absolutely, or diverges. So we're going to start off with the sum as n goes from 1 to infinity of -1 to the n plus 1 over n plus 1. So the first thing that I like to do is look for the absolute convergence. So we're going to look at the sum as n goes from 1 to infinity of 1 over n plus 1. So we're getting rid of that alternating piece. So we can compare this with a p-series. So we're going to compare with the divergence p-series. The sum as n goes from 1 to infinity of 1 over n. Now, I tend to like the limit comparison, so that's what I'm going to do. I'm actually going to switch, instead of writing right now, I'm just going to show you my answers on this, just for time's sake, because it's going to take a little while to write all this out. So if we look at the limit comparison, then I can take the limit as n approaches infinity of 1 over n plus 1 divided by 1 over n. So that limit as n approaches infinity is really just the limit as n approaches infinity of n over n plus 1, because we can simplify our fractions. Since they have the same exponents, we can look at the coefficients and we get 1. So this diverges by the limit comparison test, because remember, with limit comparison, if we get a positive finite value for the limit, then the two series do the same thing. Since we knew that the first one that we chose was divergent, that means the other shall be divergent as well. So we know it's not going to converge absolutely. So now we want to look to see whether it will, it's not going to converge absolutely. Now we want to see if it converges conditionally. So then we have to do the alternating series test. So the limit as n approaches infinity of 1 over n plus 1 is equal to 0. Yay! Then we look at the terms. 1 over n plus 2, so that's the n plus first term, is actually less than or equal to 1 over n plus 1 for all n greater than or equal to 1, so it meets both conditions. Therefore, it converges by the alternating series test. Therefore, the series converges conditionally. So check for absolute convergence by looking at the series that doesn't alternate. Then check for conditional convergence if it is not absolutely convergent. So now let's look at another one. So we're going to look at the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 5n plus 2 over n plus 7. So again, we're going to look for absolute convergence first. Again, just to save time, because it's taking me a long time to write with my left hand, I'm going to just put up my answer here. So what I'm going to do for this is the nth term test. If we look at this, we can easily take the limit of this piece, and we see that the limit is going to be 5, because again, the exponents are the same, so we look at the coefficients, we get a 5. It's not equal to 0, therefore it diverges by the nth term test. Since that piece diverges, it does not converge absolutely. So then we want to look for conditional convergence. So we use the alternating series test. However, we know that the limit as n approaches infinity of the a sub n term is not equal to 0, therefore it diverges by the alternating series test, so it does not converge conditionally, it does not converge absolutely, the series simply diverges. And then we've got one more. We've got the sum as n goes from 1 to infinity of negative 1 to the n plus 1 over n to the 4/3 power. So for this one, again, we'll check for absolute convergence. So we want to see whether the sum as n goes from 1 to infinity of 1 over n to the 4/3 converges. So we can look at this as a p-series, because it is. The p-value is 4/3, which is greater than 1, therefore it converges. Since it converges, since the absolute value converges, we know it converges absolutely. Absolute convergence is stronger than conditional convergence, therefore we are finished. The series converges absolutely.